Hi everybody, this is Austin Hoggett here to give you another lecture from OpenStack's Intermediate Algebra. Today we're going to continue the conversation around simplifying radical expressions. We're going to learn about something called the product property and the quotient property. These techniques allow us to simplify radical expressions that can't be done using just the definition. Previously, if we wanted to find something like the square root of 4, for instance, we posed the question, what raised to the second power gets me back what's under the radical? We found that there was what's called the principal root and just the opposite. So we might find an answer like plus or minus 2. Instances where we can't find, based on this definition, a solution are what we'll talk about today. So while the square root of 4 can be easily found because it can be written with an exponent like this, we won't always be able to do so. For instance, I know that the square root of 4 is 2, and that the square root of 9 is plus or minus 3, but how would I find something like the square root of 7 or the square root of 8? So let's talk about this first property. The product property tells me how to factor in such a way that I identify two things: perfect nth factors and what I'm going to refer to as trash factors. Okay, so what is an nth factor? Something like 16, for instance, could factor into 4 times 4. While 16 itself is a perfect square, so if we asked what's the square root of 16, we'd be looking for a way to rewrite it as something to the second power. Therefore, we can call it a perfect square factor. What's a trash factor? Well, let's take 8, for example. 8 could factor into 4 times 2, where 4 is the perfect square, but 2 isn't. We would refer to this as the trash factor. So trash factors in this case just refer to terms that can't be written as perfect squares, perfect cubes, or any other order term. So what is the product property? The product property says that if I have the nth root of some expression, I should be able to factor that expression into two parts. I referred to these earlier as the perfect nth factor and the trash factor. So an example you'll see here in just a moment is at the bottom, where we're looking at the square root of 5 and the square root of 2, or excuse me, the square root of 12. So for instance, the square root of 5 is prime, and so the factors are kind of boring. We get the square root of 1 times 5 as an equivalent for that statement. The product property here allows me to then split each of those factors into their own radical. And so we would say this is equivalent then to the square root of 1 times the square root of 5. While the square root of 1 is a perfect factor, meaning we can use our definition of the root to answer the question, the square root of 5 isn't. And so we really just end up back with, well, the square root of 5. Since the square root of 5 is some irrational value, we can punch it in our calculator to get some sort of equivalent in terms of a decimal, but it's not going to be exact. The square root of 12, however, has a slightly different story. When we go to factor the square root of 12, again, we need to think about what are the perfect square factors and what are the not perfect square factors in that expression. We'll look at some more advanced techniques on how to identify these a little bit later. For now, I'll go ahead and tell you that we're going to split square root of 12 into two factors, the square root of 3 times 4. In this case, 4 is our perfect square factor. It can be written as a square term. And the square root of 3 is our trash factor. It's going to stay underneath the radical. So when I go to split these, again, I'm going to separate them into their own radicals, my perfect square and my non-perfect square. The product property is what allows me to do this. And the reason we separate them like this is so that we can use that definition of the root to answer the question for our perfect nth factor. Again, the square root of 4 is going to be 2, at least the principal root anyway. And then we just multiply by our trash factor, which stays underneath the radical, square root of 3. So originally we would have posed the question here, what raised to the second power gets me back what's under the radical? Well, this is the answer to that question. 2 square root of 3 is what I raised to the second power to get 12. So we use this technique in lots of instances where, again, our original expression isn't immediately something that can be written as a square or cube or fourth or fifth root term. Let's look at some more examples. Remind yourself that the process we're looking for here is identifying those large perfect square expressions. It can be kind of difficult to do so. So we'll look at some instances where I have numeric and variable terms underneath the radical, and we'll talk about how to procedurally at least go about finding all these perfect square expressions. So let's take a look here at these two examples. I'm asked in part A to find the square root of 500. And so 500 itself is a quite large value. It's maybe not obvious to you what the largest perfect square or non-perfect square would be. So what I'm interested in doing, again, is separating it into two parts. My perfect square factors and my trash factors. Now, for my sake here, I'm going to draw this as, well, a perfect square and a trash can. I want to know what is 500 equivalent to, a perfect square times a non-perfect square. So if you're not quite sure, we can use what's called prime factorization to start this process. I don't need to know exactly what the perfect square and non-perfect squares are immediately, but I need to know how to break the number down so that I can find them. Remember, perfect squares just means something that can be written as a base to the second power. So I might start by saying, well, 500 could be broken down into 5 times 100. And that actually identifies for me the perfect square, the largest of which is 100, and the non-perfect square, 5. If it's not obvious, we can continue this further and say, well, 100 breaks down into something like 25 times 4. Now, you might recognize 4 as a perfect square, and so when we go to factor this thing, we can put it into that box. Remember, perfect squares in this case just means any factor that's duplicated. Let's actually go all the way to the prime factors here for 500 to demonstrate this. If I continue to break things down, we might say 25 is just the prime number is 5 times 5. 4, of course, is just 2 times 2. And so underlining here all of my prime numbers, the way that we could rewrite 500 is the product of all these primes. So duplicate values represent perfect squares. And if you multiply a perfect square times another perfect square, you just get the largest in the bunch. So right here we have the perfect square 4. Here we have the perfect square 25. 25 times 4 gets me to 100. And again, that goes inside my perfect square box. The other factor that's left over goes in the trash. So those are the factors that we're going to use our product rule on to be able to find the root. So again, the square root of 500 is going to be equal to the square root of 100 times 5. If we give each of those their own radical, we get the square root of 100 times the square root of 5. So what is the square root of 100? Well, what value do we raise to the second power to get that value? Well, in this case, it happens to be 10. So we're left finally with 10 square root of 5 for our solution. Part B, we can do a similar process. But you have to be cautious here when looking at the index. Since we were looking for square roots or perfect square factors in part A, we were looking for duplicates. In part B, when we start looking at the factors of 16, we're now looking for perfect cube factors. And so here we have to identify triplets inside the prime factors of 16. Breaking it down again without knowing ahead of time what those factors are, I might say this is 8 times 2. And of course, 8 is just 2 times 2 times 2. So 16, as far as its prime factors go, is just 4 2's multiplied together. So 3 of these make up a perfect cube. So if I want to split this into my perfect cubes and my non-perfect cubes, we'll end up with 8 times 2 being split into their own radicals. What raised to the third power gets me back what's under the radical would be how I'd pose the question for my perfect cube factor 8. And the answer happens to be 2. So finally we get an answer here. The cube root of 8 is 2. The cube root of 2 stays under the radical, and we have our solution. Again, prime factorization is really helpful in identifying those perfect square, cube, fourth, or fifth factor terms. It just takes some getting used to and remembering that the index indicates how many factors that I'm looking for. Recall last time when we talked about introducing variable expressions as well, that we used a sort of pro tip here that if I have something like the nth root of some expression b to the m, we could rewrite this as a fractional exponent or a rational exponent. And that helps in a lot of ways to identify solutions. So for instance, in part A, I'm asked to find the square root of x to the third. I'm really still interested in identifying, again, what is the perfect square factor and what is the non-perfect square factor. So it's a little bit more conceptual here to identify perfect square factors for a variable term. When I factor an exponent like this, we usually just expand it to multiply the base together. So x to the third really just means x times x times x. Remember, duplicates represent a perfect square, so we could factor this into x to the second power times x, where x squared is my perfect square term, and x goes in the trash. In other words, since my exponent was not evenly divisible by the index, I just threw one of the exponents away and made it even. So we could split this up into, again, the square root of x squared times x, and then give each of those their own radical. So the square root of x squared is just x. The square root of x stays underneath the radical, and there we have our solution. So in parts B and C, we could do a similar type task where we want to factor in such a way to take advantage of our shortcut. In other words, if the index is not divisible by, if the exponent of our variable is not divisible by the index, we throw enough of those factors away such that it will be. Take a look at part B.